Hello everyone, welcome to this lecture for chapter 3, Data and Signals. For this lecture, we're going to follow the slides from Data Communications and Networking 5th edition by BracU. So far, in chapter 3, you guys have talked about data and signals. We have talked about periodic analog signals, how the periods work. We talked about digital signals as well, and there are different kinds of transmission impairment. We talked about those transmission impairments and how to solve them. Now, in this video, we're going to talk about the limits of data rate, the rate in which we can pass the data from sender to receiver. And in the next video, we'll talk about the performance. So let's start. So one of the important considerations of data communication is that how fast we can send data. And by fast, I means how many bits per second we can transmit over a channel. The higher the number, the faster the network is. So there are two theoretical formulas that we're going to learn in this video that were developed to calculate the data rate. One by Nyquist, which was done for a noiseless channel, and another by Shannon, which was done for a noisy channel. So before going into the details of the Nyquist and Shannon theorems, let's talk about noiseless and noisy channel first. So when we talk about the term noiseless, we actually mean there is no noise in the transmission medium. For example, let's say if you have a device A and if you have another device B in which you want to send some data, we are assuming that in the medium or the link that actually connects device A with device B, we are assuming for a noiseless channel there is no noise. So that means if A wants to send 100 bits of information, B will receive exactly 100 bits of information without any noise. However, in a noisy channel, B will not receive all the 100 bits that were actually sent by device A because there will be some noise added to the received bits. So this is the main primary definition of a noiseless and noisy channel. It's pretty much straightforward. You can know which channel we are talking about by the name. Noiseless means without any noise, and noisy means there will be some noise in some capacities. So basically, when we talk about the channel capacity, the capacity means how much bits that can be transferred from device A, which is sender, to device B, which is receiver. So in case of noiseless channel, we are actually sending all the bits. Like for example, if the receiver wants to get 10 bits per second, the sender only needs to send the data 10 bits at a time per second. Because there is no noise, the channel capacity is theoretically 100%. But however, for noisy channel, the channel capacity will not be 100%. It will be somewhat less than 100%. The higher the noise, the capacity will be lower. For example, if let's say if the noise is 20%, that means the receiver can only receive up to 80%. That means the channel capacity is maximum 80%. Then again, in another example, if the noise is higher, let's say the noise is, let's say, this much, 35%, this will mean the channel capacity will be less. In that case, the channel capacity will be only 65%. So there is two theorems or formulas to calculate the channel capacity for both noiseless channel and the noisy channel. So the main purpose of this video is to get yourself introduced with the theorems. For noiseless channel, we have Nyquist formula, and for noise channel, we have Shannon capacity. Okay. Now, for noiseless channel, we usually calculate the Nyquist bit rate formula, which defines the theoretical maximum bit rate. Why? Because we're assuming there is no noise. That means the channel capacity is 100%, which means the bit rate we are getting using this formula is the maximum bit rate. And why this is called theoretical? Because we all know that in real life there is no such thing as noiseless channel. There will always be at least some portion of noise in the medium of the channel. So that's why the bit rate we calculate using Nyquist formula is actually defines the theoretical maximum bit rate. And what's the formula? The formula is very straightforward. If we want to calculate the maximum bit rate, which is denoted by B, or maybe let's say BR, which means bit per second, that will be 2 times the bandwidth times log 2 base the number of level. Here L means the number of levels in the signal. Okay, so in the previous video we have already talked about levels in the signal. We know that, like, usually if the two level signal looks like this, 0, let's say this is 1 and this is 0, or sometimes there can be multiple levels, like let's say if we have 4 levels, we need 2 bits, right? This one will be let's say 0 0 0 1, let's say, or maybe this one is 1 0 1 1. Anything is fine. So basically the number of bits you need is actually defined by the number of levels. If the number of level is 2, you only need 1 bit, right? Why? Because 2 to the power 1 is 2. If you need 4 levels, that means you need 2 bits to represent each levels. Why? Because 2 to the power 2 is 4. So that means if you need 8 levels, you need 3 bits per level, because 2 to the power 3 is 8. Okay, so this L means the number of level, and this is the bandwidth, and this 2 is with the formula. So let's try one example. Here in this example 3.34, we are considering a noiseless channel with a bandwidth of 3000 Hertz. Okay, so let's write the information here. We have bandwidth which is 3000 Hertz, or we can say 3000 per second, right? Okay. Now the signal level is 2. That means the number of levels is actually 2. Now if we want to calculate the maximum bit rate, which is BR, or you can say it's the maximum bit rate, that will be 2 into B into log 2 base L, which is 2 into 3000 per second into log 2 base 2 bits, which will mean 2 into 3000 into 1 bits per second. So that means the answer will be 2 into 3000, 6000 bits per second. Now this bits per second is actually written as BPS, which means bits per second. We know this BPS because when we calculate the bandwidth of, let's say, our home Wi-Fi, we calculate using either kbps or maybe mbps, or if you are residing in, let's say, in any advanced countries, it might be gbps as well. So this is how we calculate the bit rate, the maximum bit rate of a noiseless channel. You can see one thing, that we are not using any noise calculation here because the channel is the noiseless channel. So that means whenever we are using Nyquist formula, we are always talking about the noiseless channel. Okay. Now, if the signal level is 4, that means, I talked about this in the earlier slide, but I'll talk about it again. If we have 4 levels, let's say this is level 1, this is, let's say, level 2, let's say this is level 3, and this is level 4. Now we only have zeros and ones, right? But now we have 4 levels. That means using either only 0 and 1, we cannot actually describe all the levels. That means we need another bit, let's say 0 0 0 1 1 0, and let's say for level 4 1 1. That means for each level we need to send 2 bits. The higher the level, the higher number of bits we are sending each level. So be careful about this. If the example said 8 signal levels, for example, then for each level we will send 3 bits. Why? Because 2 to the power 3 is 8. So these are the 8 levels that we'll be sending in those cases. 1 1 0 0 1 0 1 1 1 0 and 1 1 1. Okay, so this is really important. Okay, so now in our example we are talking about 4 signal levels. So that means in each level we only need 2 bits. Now if we want to calculate the maximum bit rate, how can we do it? This is the example. So the bit rate BR will be 2 into B into log 2 base L. Here the bandwidth is given because it's the same noiseless channel as before. That means the same bandwidth as the previous channel, because bandwidth is always fixed, right? So it will be 3000 hertz or 3000 per second, and then log 2 base 4 bits. That means what? 6000 into 2, which is 12,000 beats per second. So think about it. Everything was same, the bandwidth was same, but the level was doubled, which made the maximum bit rate double. Previously it was only 6000, right? Because we only had 2 signal levels. That means we are sending 1 bit per level, but here we're sending the double amount. That means 2 bits per level. So that's why this one, the bit rate increased to 12,000 bit per second, which can also be written as 12 kbps. Okay, fine. Now sometimes we need different kinds of explanation for Nyquist. Let's say in this example you are already given the data rate or the bit rate you want to get, which is 265. Okay, so that means we already got the BR, which is 265,000 beats per second. Okay, and now it has a bandwidth of B 20 kilohertz. That means 20,000 per second. Now the question wants you to calculate the number of signal levels you need. So we can use the Nyquist formula, which is BR is equal to 2 into B into log 2 base L. So you have the BR, you have the B, you need to find out the L, right? We can easily do it. Now think about it, because when we're using the Nyquist formula, right, because this number is not a power of 2, right? So that means in the log, as we have 2 base, we'll not get the correct levels. We'll get a decimal value, right? So what we can do is we can increase the bit. Like we need to send 265 kilobyte per second. We can go up to the next number, which can be written as 2 to the power n, right? So the next value, which can be written as 2 to the power n, is actually what? 256 was the previous one, and the next one is 512, right? So by this formula we can actually increase our bit rate. For example, the result is not a power of 2, so we have to either increase the number of levels or reduce the bit rate. So if we increase the number of levels, let's say if we have 128 levels, that means the bit rate is 280 kbps. And if we have 64 levels, the bit rate will be 240 kbps. So that means in this type of example, what you have to do is when you have decimal value 98.7, that means it's not divisible by 2. So we have to make it divisible by 2. And what's the closest value which is divisible by 2 for 98? If we go down, it's 64. If we go up, it's 128, right? So if we use 64, for example, then the total bit rate will be 2 into 20,000 into log 2 base 64, right? And if we use 128, the formula will be 2 into 20,000 into log 2 base 128. If we use 64, the bit rate will be 240. If we use 128, the bit rate will be 208. Okay. Now, we talked about noiseless channels till now, but in reality, we know that we cannot have a noiseless channel because the channel will always be noisy. It doesn't matter what kind of devices you are using, what kind of protocols you are using, what kind of advanced transmission medium you are using, there will always be a small percentage of noise. So that means the channel in reality is always noisy. So the thing we learned about Nyquist formula is it does calculate the maximum bit rate, but this bit rate is also theoretical, it's not practical. So in reality, in 1944, Claude Shannon introduced a formula which is called the Shannon capacity to determine the theoretical highest data rate for a noisy channel. Okay, that means now we are considering the noise factor. So the Shannon capacity formula was the capacity of a channel is bandwidth into log 2 base 1 plus signal to noise ratio. So I hope you already know about signal to noise ratio, which is basically what the name suggests, is signal by noise, right? Signal by noise. So we talked about this in the previous video. If you have already forgotten about it, no problem, we're gonna discuss it in this video as well. So let's consider one example, 3.37. Here they have considered an extremely noisy channel in which the value of signal to noise ratio is almost 0. So that means the SNR value is almost 0. When the SNR value will almost be 0, think about it. The SNR is basically signal divided by noise, right? So if this noise is so strong, the noise is so much higher value that this value almost becomes negligible. So in those cases, the SNR will be close to 0. That means if the SNR is less or close to 0, that means the noise is actually higher. Okay. So in that case, this is an extremely noisy channel. So here you have been asked to consider an extremely noisy channel in which the value of signal to noise ratio is almost 0. And when we know that SNR is almost 0, we know for sure that the noise is so strong, the noise value is so high that we are getting negligible amount of signals, right? So in this kind of channel, if we want to calculate the capacity by using this formula, how can we do this? Capacity is actually the bandwidth, right, which is B. We don't know the actual value, but we don't need that. Just wait for a couple of seconds. Then we'll have log 2 base 1 plus SNR. And if the SNR is almost 0, we can write is B log 2 base 1 plus 0, 1 plus 0, which is B into log 2 base 1. And we know that log 2 base 1 is equal to 0. So that means B into 0 is 0. So that means what? That means as the bandwidth is a fixed amount, the capacity of any channel is directly proportional to the signal to noise ratio. That means if the noise is so much high, it doesn't matter what your bandwidth is, you won't get any bits. You won't receive any data through this channel. So that means the capacity of the transmission channel is directly proportionate to the signal to noise ratio. It does not matter. You can have a very high bandwidth, but if your signal to noise ratio is very high, you will not receive any data. Okay, this is very important. Now let's try to calculate one theoretical highest bit rate for a regular telephone line. And it says here that a telephone line normally has a bandwidth of 3000 hertz. Okay, now the signal to noise ratio is usually this amount. You are asked to calculate the capacity. We know that, right? The capacity is actually bandwidth into log 2 base 1 plus SNR. We have all the values, right? 3000 per second into log 2 base. SNR is 3162. That means we have 3163 bits. And this will be your answer, whatever the value is, right? So the value is what? The value is 3000 into 11.62, which is 34,860 bit per second, which can be written as 34.86 kbps, right? Simple. So if we want to send data faster than this, we can increase the bandwidth or we can improve the signal to noise ratio. In both cases, the data rate will be higher. All right, sometimes you also know this from the previous video is that sometimes the signal to noise ratio is given in decibels. So in that case, we have to convert it to signal to noise ratio. Be careful. Because signal to noise ratio in database is not the same as signal to ratio. Okay, why? Because signal to noise ratio is actually 10 to the power signal to noise ratio in database in decibel by 10. So in your question, if you are given signal to noise ratio by decibel, you cannot use the Shannon capacity, because in the Shannon capacity you have to use the SNR value. So if you are given SNR decibel, you have to first convert it into SNR using this formula, and then you get the value, and then you will use that value here. Okay, so be careful about this. Signal to noise ratio in decibel is not the same as signal to ratio. Okay, fine. So when the signal to ratio is very high, you know that we can actually assume that SNR plus 1 is almost the same as SNR. Let's say your signal to ratio in noise ratio is 10,000, for example. In that case, SNR is 10,000 and 1 plus SNR will be 10,001. So if you log to this value and if you log to this value, those value will be really close. So when the SNR is very high, you can actually ignore this 1 plus SNR, and you can simply write for bit rate bandwidth into log 2 base 1 plus SNR. If the SNR is very high, you can actually assume that this means B log 2 SNR. Okay, this is only when the signal to noise ratio is very high. If your signal to ratio is very low, let's say your signal to ratio is, let's say, 1.2, in that case you cannot assume that 1 plus SNR is SNR. But for higher values, the log 2 value will be mostly same. Okay, fine. So in practice, we need to use both methods to find the limits and the signal levels. Okay, so let's go with an example. We have a channel with 1 megahertz bandwidth. That means the bandwidth B is 1 megahertz, which is 10 to the power 6 hertz, which is 10 to the power 6 per second. Okay, and the SNR for this channel is 63. All right, what are the appropriate bit rate and signal level? How to calculate this? First use the Shannon formula to use the capacity, which will be what? The capacity will be 10 to the power 6 into log 2 base 1 plus SNR is 1 plus 63, which is 64. That means 6 megabit per second. Okay, now what we can do, we already got the theoretical maximum capacity, right? The Shannon formula, this is the upper limit, right? This is the highest max, this is the maximum capacity, right? Now for better performance, we will choose something lower, obviously, because we have to consider about the noise. So let's choose something lower, let's say 4. You can choose 5 as well. We're just choosing 4 here just to show you one example. Now if we use the Nyquist formula, we'll get the number of signal levels. How? We got the bandwidth, which was 6, but we're considering something low, which is 4. So the Nyquist formula is bit rate is equal to 2 into bandwidth into log 2 base L. We got the bit rate, which is 4. We got the bandwidth, which is 1 megahertz. We can easily calculate the value, which is level, which is 4. Okay, fine. So that was all for this video. I know this formula can get a bit tricky, but the main cheat sheet is whenever you have the SNR value, that means we are considering a noisy channel. In that case, you'll use the Shannon capacity. And when we are talking about a noiseless channel, that means we don't have any SNR values, we don't have any noise. In that case, we'll use Nyquist. Okay, so the cheat sheet is actually for Nyquist, formula will be used when we have noiseless channel, and Shannon will be used when we have a noisy channel. Okay, fine. So in the next video, we'll discuss about the performance measures like the bandwidth, latency, throughput. This kind of things will be discussed in the next video. So I hope you are doing well in this pandemic situation. Thank you for watching this video, and goodbye.